Recording.
Recording in progress.
There it is. Forgot to do that last time. Okay, so everyone can see the screen, right, on Zoom? The one. Awesome. Okay, so as I wrote up here, I always have to say this, do the sign-in thing, just so ACM knows you were here. That's how they sort of track attendance and everything. You should be able to scan that QR code. There have been problems in the past with like it being on a projector that messes it up. So here's the link. I tried to keep it simple. But just go to that link and it'll like let them know that you were here. You don't have to fill anything out. Okay. So today we're talking all about memory. There are sort of three main components that we're interested in, and they sort of vary in, I guess, level of detail, starting from like the most abstract, which is the heap, down into the sort of middle one, which is the stack, and then like what's actually happening on the hardware. I mean, the stack is actually happening on the hardware, but the way that operations are performed, which is registers. So we're going to try to look at all three of these. I want to get through them all today, but at the same time, I think this is like maybe the most important topic we'll be talking about, just because it's like so fundamental to learning how to write good code, I guess, like knowing what's actually happening, that I don't just want to blaze through it all, right? So we'll try to get through it, but it might sort of bleed over into next week's lecture. Okay, so most of the examples I'll show, probably all of them actually, will be in C/C++, just because, and then there will be a little bit of assembly at the end, just because that's like, it allows you to do sort of everything. But I will also talk about how this all applies to other languages, mainly Java, because Java is just sort of a placeholder for Java, C#, JavaScript. Most of it is the same. Okay. And another thing I should define is the term like a descendant. Is that an A or an E? Let's see, descendant of C. Because I say this a lot, definitely in this lecture and in every other one. So these are pretty much the following languages. The two you'd expect, C++ and C#. Java, certainly. I consider JavaScript a descendant of C. It is very different, but also like a lot of it is the same. So that one is sort of, optional. But essentially, these are just like the main imperative languages. And that's what we'll be talking about. I don't have almost any experience with functional programming, which is sort of the other big paradigm. In that one, though, memory tends to be something that you, as the programmer, don't really think about even. Like you rarely have the ability actually to think about it. It's more of like specifying computations, and the computer figures out how to perform those, and it sorts out all the memory for you. But in these imperative languages, like the way you write code in them is basically by assigning things to variables, doing operations with those variables, and moving stuff around in memory. That's like what you do. That's how you perform computations. And because of that, you're just like straight up, you're forced to interact with the memory model of your computer. That's just how it works. And so knowing how it works will just make you better at all of this stuff. I'm going to try and scroll. There we go. Okay, so in particular, I said like the way you do stuff is by assigning values to variables. In particular, I'm talking about variables of the primitive types. So these are basically what you'd expect, just sort of all the integer types. So bool or boolean, byte, char, short, int, long, all that. Floating point, so float and double. And then also in C and C++, pointers and references. They are a bit weird because they're sort of like type modifiers, but under the hood, pointers and references are just pointers. They're just, on 64-bit systems, there are 64-bit memory addresses. So they're the same size as most of these other ones, like long and double. So these are the primitive types. And you can have more complex things. In C and C++, we have structs. We also have classes. In Java, you have classes. In JavaScript, you have classes. But those classes are they're just inevitably composed of these primitive types. So this is really like what we're going to be talking about today. Okay. So we will start. I wanted to structure this so that it would go from like highest, most abstract level of memory down to the hardware. But it didn't quite make sense to do it that way. So we're sort of doing it in a weird order. We're going to start in the middle and then look at the most abstract and then look at the hardware, which probably also isn't the best way to do it, but that's just how it worked out. So we'll start by considering the like fundamental properties of local variables in the C languages. So what is a local variable and how do they work? Well, we have a couple like guarantees about local variables that you probably never really think about, but that are always true and are very important to understanding what's actually happening. So number one is that we can have a theoretically infinite amount. Obviously, it's bounded by the amount of memory you have in your system, but the language itself specifies no limit on the number of local variables you have, and the computations involving those variables have nothing to do with the number of them. So for all intents and purposes, we can have an infinite number of local variables. And the second thing about local variables, which is just inherent to the name, is that they are local. They can't be accessed by other methods from the outside, basically. And this is something that like is just seems so blatantly obvious. Like, why am I even telling you this? Everyone knows this. This is like the first thing you learn when you take CS 101. But it's useful to, and it'll sort of introduce us to a useful mental construct to actually consider why these two things are true. And now the second point is the main one. So this is what we'll be focusing on. The first point, the fact that you can have an infinite number, is sort of just like a byproduct of the way that the second one is actually implemented. Okay, so we will start. I might want to close that door. Can you do it? Awesome, thank you. Okay, so we'll start by considering the stack. The stack is where local variables are stored. Now, there is going to be a good amount of confusing terminology in this because, I mean, as I'm sure you're aware, int A, int X, int B, int C, computer scientists aren't great at naming things. And so they sort of just like use the same words for very common data structures to describe these underlying memory principles. And there are reasons for that, but it's still confusing. So the stack, it's important there that I'm saying the stack. Whenever people say the stack, they're referring to this part of the hardware. And as I mentioned, it is actually like the name is related to the data structure. It operates as a stack. If you don't know what a stack is, I'll just give you like a 15-second rundown. It's usually just an array, just some contiguous memory. It could be a linked list, but it's usually an array. And you can only add and remove from the end of the array. And the end is, when you're talking about a stack, the end of the array is usually called the top of the stack. So think of it like a stack of papers on your desk. You put stuff on top, you take stuff off the top. And this is where local variables are stored and also used to control like the entire execution of all the code running on your machine. The stack is like incredibly important. There's so much stored there that unfortunately we probably don't have time to talk about. I might come back to it at the end once we sort of drop down into assembly. But for now, the stack is just local variables. That's all you need to know. Okay. Now, the sort of mental construct I was talking about is this concept of stack frames. So usually when we draw, when we're thinking about the stack, we're thinking about various method calls and the state, the local variables that each method contains, and sort of the overall state of our program. It's useful to look at it in terms of the stack. It sort of helps position things in your mind. So a stack frame is sort of just a little box. We assume this is like the base of the stack. It's not really important. It's just drawn as a horizontal line. And then everything grows up from here. So, in Java and C and C#, the main function is the entry point of your program. So that will always be sort of the bottom of the stack. That's the first frame on the stack. And then any methods that main calls, or any functions that main calls, will sort of push a new frame onto the stack. Push meaning add it to the top. So if I'm trying to print something out, my main function might call printf, and then that calls a whole bunch of stuff. And so essentially what a stack frame is it is just like a graphical representation of a single invocation of a method. And what I mean by invocation is if we consider recursion, like say I have some fib function here, which has a base case, and then it calls itself, right? Return fib of n-1, so if my main function calls fib, then if n is greater than 2, fib is going to call itself at least one more time, and we sort of just keep going up. And so that's why I said one invocation, because methods can call themselves, methods can have the same name. So usually you think of this as like an instance of a method being called. And in addition to the name, we usually store, or we write here, like the local variables and their values. So main might have no local variables. Let me just write like an example main method. Maybe it just calls fib of 5, something like that. Okay. And then that's using this sort of half definition of fib up here. So in this first call, n will be equal to 5. And then in the second one, n will be equal to 4. And the one above that, n will be equal to 3. I'm sure you can see where that's going. And so this sort of, it can be useful to like actually draw this stuff out. In very rare cases, usually it's with recursion. And if you're sort of new to recursion, it's good to draw this all out so you can see, I guess, just the pattern that things are executed in. But usually you're not going to be drawing this out by hand. You're just you're going to be thinking of it, like having this idea, this sort of graphical representation just in your mind's eye of what happens when you call a function is very useful. Okay. And one of the reasons it's useful is that even now, even with just this basic explanation, we can sort of see why this main point about local variables is true, that they can't be accessed from the outside. It's because in memory, this is a very simplified version of memory, obviously, but it is somewhat true, and it maps to reality quite closely. In memory, the in variable that this fib invocation is using is different from this. Like they're just straight up in different places, and that's why this one can't access that one. A better example would be involving two different functions. So let's look at that now. So let's say I have like a super simple method called add print, and it takes in 2 integers, a and b, and then it just creates a new local variable c, which is the sum. It prints out the sum, and then it returns the sum. Okay, hopefully that's legible. And then I'll just write sort of a simple main function here. This will just, let's give it 2 local variables as well, int x equals 1, y equals 2. Then we will call our method add print and pass it x and y. And then that's the end of the main. Okay, so let's look at this on the stack. So we have our main, and this has x is equal to 1 and y is equal to 2. And this calls on the second line of main here, it calls add print. So we push a new stack frame. And now add print has its own local variables, A and B, but we've assigned them to the values of X and Y. Now, the reason that I'm only talking about primitives right now is because fundamentally what's happening here, which hopefully we'll get to this today, is that the values of x1 and x2, like you can think of it as being copied into the values A and B. So we've passed x here in the A position. So A will be 1, and then Y, or no, not Y. B will be the value of Y, which is 2. So we have our own local variables where we copied the values of those. Good. And then, this prints it out with printf. That probably calls a bunch of stuff. And then eventually it will end at some point, right? Like at some point, there's a method that doesn't call any other methods, and then everything starts returning. And at that point, these stack frames are popped off the stack. That's what we call it. I don't know how to use OneNote very well, so I don't think I have like an array. Oh, there we go. I do have an eraser. So they're just popped off. And of course, because it's a stack, you can only add to the top and remove from the top. So that's what's happening here. We just sort of remove them in the reverse order that we added. Oh, and then also I forgot to add this, but it's not super important. Add print has another local variable C, which is 1 + 2. Okay. And then when we pop off, when add print, when this method ends, it returns a value. So we pop that value off, or we pop this stack frame off, and we sort of copy that value down to some point in main. In this case, I actually haven't assigned it to anything. So, this is just sitting in a register somewhere and it's not being used, which is fine. But just for the sake of example, I will assign this to Z. So at this point, we're on this line, by the way. Like all of this is happening when we hit return C. So the value of C is copied into Z in the calling stack frame, and then all of this is destroyed. That entire frame is popped off the stack, and we are just left with the result in Z in our main function. Okay, still pretty simple. Let's look at a case where there are some pointers involved, because that's where things start getting interesting. But the main thing I want you to notice from this is that values can very easily be passed up the stack. Up meaning that way, up, by just passing those values as parameters to whatever function you're calling. Those functions will sort of copy those values, and then they have access to them, right? So let's look at another example of passing values up the stack. I'll have, let's do this one first. Okay, we'll just do like a method that prints an array, just an integer array. We give it a pointer. I'll give it a bad name, B, just so that it's different. And then all we're going to do here, we'll just assume that it's like 5 elements long. So we'll just loop from 0 to 4, and then print, I won't write it all out, print B at I, and then that's all. And then in main, we will have an array, I'll call this one A, 5 long. We'll just 0 initialize that, and then print R on A. Okay, so in this case, we have pretty much the same thing as the last one. There's just a pointer involved. So we have our main. And within main, we have variable A, which is an array. So this is sort of a big chunk of memory that exists entirely within the stack frame of main. Okay, and then the next line we call print array. So we pop that, or sorry, we push that onto the stack. And now notice the way that this is passed. So when we call print array, we're just passing A. But remember in C and C++, if you have some array variable like this, the identifier A is sort of equivalent to this expression. That is, it's a pointer to the first element of the array. So really what we're doing here, even though it looks like we're passing an array, we're just passing a pointer. And the value of that pointer, the memory address that that pointer contains, is being copied into B in this stack frame. So B equals A. And then in here, so B equals A in the sense that it points to that memory down there. And then we just loop through it, print everything out, and return. That's it. Very simple. And this works because in this case, once again, we are passing values up the stack. But let's take these methods here and sort of reverse the roles just a bit, where our main method will do the printing, and the function we call, we want that to create the array. This is something that comes up quite often, is you want some sort of external function to do memory allocation or just initialization or something else. So we'll have this a new function which returns a pointer to an array, create R. And same thing, this will just make a stack allocated array of length 5. We can zero initialize it if we want, and then we'll just return A. And then in our main function, I'll assign this to pointer B. Actually, yeah, whatever, that's fine. To create R. And then here, we'll do the printing, just that same for loop. I don't want to write that. Okay, so if you've done like any sort of programming in C and C++, you probably have immediately identified that this is not valid. This like won't work. But using this sort of model of the stack and stack frames, we can actually figure out why it doesn't work. So as always, we start with our main method. And here we have some value B that we are assigning to the return value of create array. So our very first line, we're calling this other function, create array. Okay, and then now the roles are sort of reversed. So A is now a contiguous chunk of memory in create arrays stack frame. And then all we're doing is returning that pointer. Because remember, A is a pointer to the first element of the array. So like there. So we take A and we return it to B. But remember, when we return from a method, we pop that method's stack frame off the stack. So what we get is this. We have B. I should have drawn this arrow the other way, actually. We get B in our main method pointing to some memory that existed in a stack frame above main that now has been destroyed. This memory has been reclaimed. It's undefined what's there. As a side note, I don't know how the computer actually uses it. I'm not sure like why it mangles all the stuff that was on the stack. Maybe it might in fact just be to prevent this kind of behavior because you shouldn't be trying to do that anyways. But essentially this points to something, but it's certainly not an array of zeros. And so we've discovered a new problem here where we know that passing values up the stack is fine, but if we want to pass them down and the value we're trying to pass down is anything more complicated than a primitive, just a single variable, we run into trouble because if it's a local variable that we've allocated within some method, it's in that method stack frame, that data gets clobbered, and then we have a pointer to something. Okay. So this is a problem, but also like it's clearly not a problem. Like this is not an unsolvable problem. You can get out of it in any language. In Java, in fact, because of the way the language is designed, you will never run into that problem. But let's see how we do that. So the answer is sort of the second part of memory that we're looking at, which is called the heap or the free store. Both of these typically mean the same thing. There might be like some implementations use one or the other. I don't know. But basically, this is just an area of memory that your program has access to, just like the stack. But it's not inherently used by the program itself. Like the stack, you know, whenever you call a method, the stack is where information about that method goes, right? The heap, it's entirely up to you. Unless it's sort of a managed language like Java, which has memory collection and all that, or garbage collection. But in C and C++, the heap, you just tell the computer to allocate some memory for you on the heap, return you a pointer to that, and then it's yours. You own it. The OS isn't going to do anything with it. And the main point of the heap is that it's not the stack. That's literally it. It's just an area of memory that is free for you to use, that is outside of the stack. Because if you think about it, this sort of solves our problem. Because let me scroll up a bit here. I'll try and keep that in frame. So now I'll just have to draw this smaller. So I'll walk through our program's execution again. So we have our main frame here, and we have B, which we're assigning to the return value of create array. And if we modify create array so that it's no longer creating a stack allocated array, we don't want that because clearly that just breaks everything and doesn't work. But it's using a heap allocated array. In C++, we could do this with int a equals a new int of length 5. You can also do this with malloc or calloc with like 5 times size of int in C. In C++, actually, you might have to cast that to an int pointer. I don't know, the type system is pretty strict. But essentially, both of these, all of these just allocate it somewhere else. It does store a pointer to it in this stack frame. So A still exists. We still have that local variable, but the array itself is not the local variable. The local variable is a pointer to the array somewhere in the heap. So we have this sort of nebulous blob of memory. We have an array in there, and A points to that. And then when we return A, we just copy the value of A into B. So, oops. So B also points to that. And then we get rid of that. We pop that stack frame off. Dang, I'm erasing everything. And then we have this. We've solved our problem. We have this memory somewhere that is not the stack. That's the important thing. And we have a pointer to it, right? And it's not a pointer to some sort of undefined location in memory. Dang. Okay. So we sort of just rewrote our array example there. I realize I sort of blazed through that, so I'll can I draw? Hello? Uh-oh, I seem to have broken it. That's no good. Let me just try with this. That one. Awesome. Okay, so I sort of blazed through that. I'll just give you a quick rundown. In C, the way you allocate to the heap is with the built-in functions malloc for memory allocate, calloc for clear allocate, which, if I remember correctly, is like exactly the same as malloc. It just sets the entire chunk of memory that you requested to all zeros. And then realloc, which takes a pointer that was previously malloced and makes it smaller or bigger, and then free, which is how you actually like release memory. And these are equivalent to the C++ operators new and delete. And those also have like the array overloads, I guess, or maybe those are separate, considered separate operators. I'm not sure, but new is basically malloc. It doesn't do any initialization, doesn't clear anything, and then delete is free. And again, I think implementation dependent stuff, like they are technically different. They may use different areas of memory, but it's the same thing. It's whenever you want to dynamically allocate something, you can use either of these in C++. Now, you may have picked up, if you've done Java in the past, that none of this stuff exists in Java. In Java, all we have is new, and we are forced to use new. In C++, if I have some structure, I'll give it another terrible name. Maybe it's an integer vector. I don't know why you'd want an integer vector, but you have that. And if I'm in, some code, I can just say a like that. And I've allocated an object, an instance of a type, an instance of a class on the stack. I can also do, if I don't want to do that, I have the freedom to do a star equals new a, like that. And that's just fine. But in Java, we're forced to do this. And that's what I was talking about. The language is designed in such a way that these problems can't occur because you, as the programmer, you have no freedom over this kind of stuff. In Java, anything that's primitive is allocated on the stack. So Boolean, int, short, char, long, float, double, byte. And anything that is an object is allocated on heap. Objects and arrays, which is related to the example I just showed. Arrays in Java kind of suck. They're like a weird, like pseudo object thing. But essentially Java just by default solves all of the problems that we just encountered so that the programmer doesn't have to worry about it. And as with everything, there are trade-offs with that. That doesn't mean Java is a better language than these other two. In this case, the performance is the trade-off. Java is famously slow. I mean, there's a lot of like technology that's come about since Java was introduced, like 1995. I don't know. I'm rambling, so I won't do that. But okay, so that's the stack and the heap, and now we're going to look at the hardware. So this is sort of like a break in the talk. Unfortunately, there's no good transition to this bit. I just stuck it at the end. And I shouldn't say what's going on the hardware because the stack is like as hardware as it gets. But registers are another component of the hardware that we just haven't talked about yet. So at UTD, for a CS degree, you have to take computer architecture, where they teach MIPS, the assembly language MIPS, which maybe is still used today, maybe in like ARM processors. But really everything uses x86. All of your desktop laptops use x86. I'm pretty sure your phones are probably ARM processors that use a different assembly language, but x86 is basically standard for any sort of non-embedded device, non-handheld thing. In particular, x86 64-bit is just like, it's 2021. It's been the standard for forever. Like everyone has 64-bit machines now. But going back way back, it was a 16-bit. It was designed for 16-bit processors and then eventually 32 for a while. But now we've hit 64 and everyone's just sort of caught up. And so I'm going to teach you a very tiny amount of x86. Just because it's useful. It is different from MIPS, but it's still similar. So if you've seen that, you probably won't have too much of a hard time. But the important thing to get from what I'm about to show you is not any x86 specific stuff, because it is very strange, I guess, to put it nicely. It's basically a mess because it's just this language that like the entire world depends on, that's had to be updated and kept backwards compatible for like 45 years. So it's a mess, but all the concepts here apply to sort of any assembly language and really anything that's happening on the hardware. Any computations. Okay, so registers are, they're basically, I guess you could think of them as variables, except you have a finite amount, like a very finite amount. There's a small number of registers. And I think it's better to consider them as like places where variables can go, because they aren't set to specific things. They're just like arrays of bits, typically 64 bits, that you can put whatever you want in and use them. So there are several different like classes or types of registers. That's not entirely true. In the hardware, I'm sure they're all the same, but assembly languages typically restrict certain registers from you so that you can't like mess everything up massively. But the most common ones are the general purpose registers. And these are ones that you can use for your computations. You can put whatever values you want in there. You can operate on those values and then, return them or do whatever else. And so I'll just give you like a list of the common ones. So we have sort of the legacy ones are these four, RAX through RDX. Some of these have special meanings, and I'll talk about those in just a minute. They added, I'm not exactly sure when they added, it may have been the switch to 64-bit stuff, but they added 8 new ones, which are much better named, R8 through R15, which is nice. And then there are a couple of weird ones as well, which are typically only used for special purpose things, but are technically general purpose. That's RSI and RDI. I'm not sure technically what they stand for, but S I think of as source and D as destination. These are used for certain certain instructions. That's the word. Okay, so these are 64-bit, all of these. They're typically used for integer stuff. In terms of floating point stuff, we now have all of these excellent extensions to the language that give us 128, 256, and 512-bit registers, which is just crazy. Like 512 bits divided by 32 bits, like the size of a float, is 16, and 16 is 4 by 4. So you can have like a 4 by 4 matrix if you're into like computer graphics or game stuff, and you can theoretically, I think the point of I think this was actually introduced mainly for this purpose. You can do all of your like 4D sort of perspective space linear algebra computations in like single hardware instructions. It's really cool. And these registers are XMM. These are not nearly as well named as the new R ones. I don't know what the MM stands for. 15 later versions have up to 31. And then there are also YMM and ZMM of the same amount, 0 to 31. So these are 128, these are 256, and these are 512. Okay, and they've sort of actually been adopted as like the default floating point registers, even though the floating point types, we just have single and double precision, which are like floats and doubles in the C languages, which are 32 and 64 bits. But you can, you can pack stuff in there and do operations on multiple things at once. That's sort of the point of it. Okay, so those are the general purpose ones. Then we have special purpose. There's probably a better name for these. That's just what I've called them. There are a couple of these, RSP and RBP. So SP is the stack pointer related to what we're talking about, and RB is the stack base pointer. So it points to the base of the current stack frame. So if we're to draw just a simple example, maybe we only have main on the stack, like RSP would point to, that would be the memory address of the top of the stack, like the end of all the memory that main uses. And then if we create another variable, like say we have int x, then that would sort of allocate more memory up here, and then RSP would be shifted up to point there. And then RBP points to the bottom of the stack frame, so sort of the end of the calling stack frame, the end of the last one. And these are useful. RBP is useful for doing sort of offset calculations, because a lot of times arguments will be passed to functions by pushing them onto the stack, rather than like sort of fitting them into specific registers, which sometimes is done and is more efficient, it's faster. A lot of times they are just pushed onto the stack because it's easier. And so RBP is used for doing sort of calculations with that, because it's just a constant value throughout the lifetime of the whole method, where if you're in a method and you push something onto the stack, then RSP changes. So it convolutes all your math. And RSP actually, I think you can't access this one. I don't think you can just like set it to 0 and then mess everything up, but I'm not sure. And then there are actually some that are totally inaccessible, at least in general, which are the R flags register and the MXCSR. I'm not sure what that's supposed to mean, but it's basically just flags for all of the AVX extensions, all the SIMD, like floating point stuff. And these are where x86 starts to get messy. These store the results of previous computations. So whenever you do some type of logical or arithmetic operation, it'll usually set some bits in one of these registers. Some of those bits are like the 0 flag. So if the result of the operation was 0, if the result of the operation needed a carry, the parity of the result, like whether or not the number of 1 bits is odd or even. I'm not sure where that's used, probably like communication or something, but I don't know. There's a ton of them. And they are the current value of these two also affect how following instructions operate. So an example is if I have, I can do like a move instruction, which just puts some value into a variable. I'll move like the value 1 into RAX, and then I'll move the value 2 into RCX. And then I can compare them. And there's like a billion different instructions for compare. One of them is test, which I'm pretty sure just subtracts the 2 operands and then sets flags accordingly. So this will do like RAX minus RCX and see what happens. So in this case, 1 minus 2, the value is not 0. So the 0 flag would not be set. I'll write that off to the side. So 0 flag is 0. This, when I say flag, it just means a single bit in one of the flags registers. But the carry flag would be set, I think, because 1 minus 2, you have to sort of carry something over because you get a negative number. Okay, and then if I have like a conditional jump down here, where say I have a label later on in my code that does some more stuff, and if the value of these 2 is equal, I want to jump to that, you would do like JE label. And this is kind of weird because intuitively, I would like to see this written as JE RAX RCX label, because it's just easier to read, right? It's like if RAX is equal to RCX, jump to label. It makes sense because we've sort of grown up being taught these higher level languages. But what this actually does is it looks at some of the flags in R flags to determine equality. So in this particular case, I think it just looks at the 0 flag because the result of a subtraction of 2 numbers that are the same will always be 0. So basically, if RAX minus RCX is 0, then we'll jump to label. Otherwise, that instruction does nothing. So it's kind of weird, but R flags is used very heavily. It's very, very important. And because of that, it's inaccessible. You can't move into R flags like 0. You can't do anything like that. There are some instructions, like specific instructions, that allow you to operate on these 2 in certain ways. I'm not going to talk about those though, because I honestly don't know enough. And the other one is RIP, IP meaning instruction pointer. So this is sort of a hint at a super important concept in computer science. Please scroll down. This is something that I think really this is like one of the main things that sort of demystified how computers work at a higher level. I'm not claiming to know everything about how computers work, but the instruction pointer, it is a number. It's an inaccessible register, so you can't mess with it. And the number is the address of the next instruction to be executed. That's pretty cool, because what that implies is that when I load my program, I'll have some like data. And then, of course, there will be like area allocated by the OS for the stack and the heap. But then I also have my code. The code that I wrote is part of this, and the instruction pointer points somewhere in there. So basically what I'm getting at is that everything that happens in a computer is just moving numbers around in various ways, whether that's doing computations on values specifically like 1 and 2, or if it's, you know, pointing to numbers that are instructions. So yeah, this one I don't like, you certainly can't access that on your own, and I don't think there are any instructions to like get it for you. I don't know what you would do with that, but like jump, sort of the conditional, or I guess also just any jump instruction will affect this value, because it says like if RAX is equal to RCX, then set RIP equal to label. And it says, okay, I'll just skip over whatever was here because my next instruction now points here, and I'll start running from there. So yeah, okay, so those are like the basic registers. Of course, as if this wasn't like way too much to learn already, it is, I don't know, 40, 45 years old. So there are different variants of each of the registers. And variant probably isn't a great word. I think it's better to describe them as aliases. So if I have like my register RAX here, that is not very straight, but whatever. So this is 64 bits, so numbered 0 to 63. Then the lower half of this is called EAX. So, but yes. Yes, it's a bit late for that, but yeah, I'm recording. Thank you. So the lower 32 bits is called EAX, and this is what we had before x86-64 came around. The upper half, the upper 32 bits, is actually not accessible on its own. You can't get to it. This is further subdivided. These 32 bits are further subdivided into, I think this one is called, I think this, okay, this is confusing, but this whole, let me number them, that'll help. So we have 0 and 16. Okay, so this is called AX. This is also inaccessible. So the sort of high half, the upper half of each one is never accessible by name. And then this is further subdivided into two 8-bit ones. That should be 15 actually. And that should be 7. This is called AL, and this is called AH. And I think you're not supposed to use AH because there are some weird restrictions on like using it in conjunction with other registers. So I don't know, but it's there. And this applies to all the other registers. So our BX, our CX, our DX, they follow the same sort of pattern. Our BP, our SP, the stack and base pointers follow the same sort of pattern. I'm not exactly sure what all the characters are for it, but the new registers are a lot nicer. So like R8, for example, is same thing, 64-bit register. But this is the lower 32 is R8D, and then that is further subdivided. The lower 16 of that is R8W. That is further subdivided, and the lower 8 of that is R8B. So these mnemonics appear very frequently. B, W, D, and Q. Mostly you'll see these in instructions. So in this example up here, where I said like move 2 into RCX, like this thing right here, I think technically that should be written as move Q RCX2. Q for quad word. So Q is a quad word. D is a double word. W is just a word, and then B is a byte. And the reason for this naming is this, looking at the sizes. So 8 byte has always been 8. Everyone knows that. The x86 instruction set was originally for 16-bit CPUs, meaning that every register on the CPU was 16 bits, typically, or most of them. I think that's how it's defined. And that's usually defined or referred to as the word size of the machine. So its roots are in 16-bit. So a word in all the mnemonics is still considered 16. A double word is just double that, and then a quad word is quad that. Yeah.
Maybe I'm recalling wrong, but it's 32 bits.
Yes, in MIPS it's all 32 bits. Exactly.
Oh, so it's different. Okay.
Yeah. It is very different. MIPS is a lot nicer than x86, but also not as widely used. Okay. Yeah, it might not be. I do remember reading something about, and this may have been a long, long time ago. It was used in ARM processors, but that might not be true anymore. I'm not sure. Okay, so the very last thing we'll do, I will run through an example in like sort of pseudo assembly code, our previous add and print example, just so we can see like, or hopefully you can see what's actually happening in the registers. So in this method, or in this example, we have like add print, which takes in an int A and an int B. I'll just write sort of the signatures here. And that's it. Okay, so our goal is to define this method. So let's assume we can actually write our code like this. So this will be like our main.cpp file. And this is all Microsoft's C++ compiler. This probably doesn't translate to other compilers, but as always, the concepts will. So this extern C marks it as, it basically just says it's defined in another assembly file. Then we have int main, which has x equals 1, y equals 2. Then we call add print, passing it x and y. And then we return 0. Okay, so our goal is to write this line, sort of the definition for this function, in assembly. Okay, so in the Visual C++ calling convention, the sort of Windows calling convention, actually, as a side note, I should probably also mention this because this is a thing you'll see everywhere. MASM, the Microsoft macro assembler, that's what I'm referring to when I say the Visual C++ calling convention. MASM is the assembler. It's what takes the text code, the assembly code that you write, and turns it into machine code. So there's all sorts of directives you can do with it, but in particular, the rest of the Visual C++ environment enforces a particular way that things are done in C and C++ code that is generated by it. And so if we're trying to write raw assembly that will interact with that, we need to adhere to those same standards. Okay, so the first thing we will do, I guess we could write this properly. This is called a code section, so .code. That's one of those like assembler directives that says, hey, here's all my code. There's also like a data one and some other stuff where you can define constants. Okay, so we've been given A and B. Those are the two arguments to this function. And the calling convention, the MASM calling convention, dictates that the first 4 integer arguments, regardless of their size, whether they are, 16, a word, a double word, or a quad word, these are passed in registers. I should write that out. The full thing, RCX, RDX, R8, and R9. And then everything after that, any more integer arguments are on the stack. They're pushed onto the stack. The first 4 floats, again, regardless of size, are in XMM 0 through 3. So a lot easier to remember. And then I think after that, again, any additional ones are put on the stack. Okay, so basically how that affects us here is that we have just 2 integer arguments, A and B. And so we will just be using the first 2 registers of this sort of list here. So A is in RCX and B is in RDX. That's actually not true. I just misspoke. Variables are assigned to these registers. No, that is true. Sorry. Okay, yeah, that's true, I think. Even if it's not true, the concept still remains, but don't quote me on that part. Okay. So we have, I'll just sort of write a comment. Confusingly, in assembly language, at least using the MASM assembler, semicolon means comment, which is like really annoying because it's like you're probably just used to hitting that muscle memory in every other language. But so we have RCX is equal to A, and we have RDX is equal to B. Okay, and our goal is to just compute the sum of them, and we'll store that. So we could say like, I'll just put it in RAX. So we'll do like, we'll do an add, that's the instruction, and the arguments we'll pass it are RCX and RDX. The convention in almost every case, I think, is that the first argument is the destination. And everything else, if there's other stuff after that, are the source or sources. But in this case, we have an add, and we've only supplied two instructions, or sorry, two operands. So this sort of expands to, you can think of this as expanding to in your mind. We have RCX as the destination operand, but then also as sort of an implicit second source. So this is equivalent to the C statement, RCX plus equals RDX. We're just adding the contents of RCX to RDX and storing the result back in RCX. Okay. So that is our value of C. So C equals A plus B. And then I think all we did with that afterwards was call printf. So I'm just, for the sake of example, I'm just going to make some assumptions about how printf works, which these are probably true. I'm assuming it uses the same sort of calling convention as our method here, meaning that the first argument will be in RCX, and the second and everything else will sort of follow this list. And in this case, what printf accepts, the sort of header for printf, is it accepts a const char pointer, and then only 3 dots, ... So this is a very, very ugly and outdated way of doing variadic arguments. Unfortunately, it's the only way of doing it in C. But essentially, I'm just going to assume here that because, like, for our use case, we're just telling it to print out a single integer. So we can assume, I mean, we can't assume, but for the sake of example, that this is how printf is defined. Okay, so we have RCX now stores the sum of those two, which is perfect because that means, well, that's not perfect because we want to print RCX. So down here at some point, we're going to have a call to to printf. Just assume we have access to that. And we need to load the proper things into the proper registers. So the first thing is a pointer, which is an integer. That is an integer, so it will go in one of these variables. And we will assume that we have the string we need to print it out stored in some variable called like S. And we want to put that in RCX. Unfortunately, we've used RCX here as the destination. So I'm actually going to change this. We will just switch those. So now our RDX stores C. And all we have to do here is like move into RCX the address of our string. Again, just assume this is defined somewhere external to this, and these little square brackets will get the address of that, put it in there. I believe that's how it works for constants. And then we call printf, remembering at this point that RCX is a pointer to our string, which is what it expects, a const char pointer. And then our dx is the int we want to print, which is also true because our dx stores C, which is A plus B. And then from there, call printf, we'll probably call some other stuff. And then the very, very last step of this, of our add and print method, is to return the result. We want to return C. And the way we do that, like a special use of the RAX register is it is the return register. That's always how it is. So we currently have the value of C, the thing we want to return, in RDX. So all we have to do is move into RAX, RDX, and then ret for return. And then, you know, if we sort of stick that in our main function here, it should all work. Okay, so I'm 5 minutes over time. Sorry about that. Hopefully you found this, if not useful, at least interesting. I promise you that as you think about these lower level things more and more often, you will see them everywhere. I like the number of epiphanies I have like every day about this stuff is insane. I'm still learning about all of it. So it's good to get thinking about it. Yes, question.
Did you say the RAX register was the return register?
Yeah, RAX is like by convention the return register.
And then was there a reason you switched C and D, the RDX, RCX?
That was just to adhere to this sort of thing I defined up here, because remember, the first parameter is passed as RCX and the second is passed as RDX. So RCX needs to be a pointer to our string and RDX needs to be the thing we're trying to print, which is C. Okay. Any more questions? Good. Awesome. Great. Thanks for coming, guys. I will see you next week.